Hello students, welcome back to PH107 Quantum Physics and Applications. Today I'm going to discuss more about wave functions and operators. But what we have seen so far, that to describe different static and dynamic properties of a quantum particle, we need a new equation called Schrodinger equation. Then we have seen that this Schrodinger equation has two important parts. One is called wave functions, or the solution of the Schrodinger equation, and the potential in which the particle is uh, present, or the particle is experiencing certain kind of potential. So what we have seen that there are certain conditions which needs to be satisfied by a function to be called as a wave function, which we have seen in the previous lecture. Also, we have introduced a new concept in quantum mechanics are related to Schrodinger equation known as operators. So let's go further and see what are the other new concepts that we need to learn before we start applying Schrodinger equation for different kind of problems. So the first concept we are going to learn today is known as expectation value. So what is the expectation value? So let's think that if we make measurements of a dynamical variable, this dynamical variable can be energy, momentum, position, on a large number of identical particles with the same wave function, then we can talk of an expected or average value of the variable. Okay, that's what we have seen in one of the lectures, that when you want to do different kind of measurements, you need to take a average value of a variable. Okay, so here also we have a wave function and we want to estimate average value, or let's say the expected value of a variable. This variable could be any of the uh, quantity, either energy or momentum or position. Okay, so how to calculate? To calculate the expected or the expectation value of a variable is done as we have seen in the case of the statistical calculation. Okay, so suppose we have a variable x and we want to calculate the expectation value of this variable for a given wave function psi. So the expectation value of a variable is written in this following fashion: x enclosed by this bracket, okay, we will see what this is called, is equal to, this variable is sandwiched between psi star and psi, and then this quantity is integrated over entire space. This is done for a one-dimensional case, and where psi star is a complex conjugate of your psi. Moreover, what we have understood at this point, that this psi is a normalized quantity. The normalization of a wave function is discussed in the previous class. Suppose psi is not normalized, then what we could do, we could divide this whole quantity by this normalization of a wave function psi. This is the similar thing you have seen in the case of a expectation or average value of a variable, when a function in terms of the distribution function was given, which you have seen a few classes back. Okay, so this is a general form of expectation value of a variable x in a given wave function psi. Okay, now if you want to estimate, let's say, the expectation value of a variable x square, then we can do the same. X square is sandwiched between psi star psi and then integrated over entire space, and if psi is not normalized, then this whole quantity will be divided by psi star psi and integrated over dx. Okay, so now we can calculate the expectation value of different variables like energy, momentum. But what we need to introduce not the energy, momentum, but their operators form. For example, like this. So if you want to estimate the expectation value of this energy, so by using the definition, let's write psi star E psi. Okay, and here we have assumed that your psi is a normalized wave function. And now what we need to do, we need to introduce the operator of this variable E, because in quantum mechanics, all the variables are represented in terms of the operator. So what is the operator form of your energy, which you have seen in the previous lecture? I h cross d over dt. Okay, so this is how the expectation value of a energy variable or energy operator is estimated. The same way we can estimate the expectation value of a momentum operator. So your psi star p psi, and now we have to introduce the operator form of your momentum operator. So this is the momentum form of the operator, momentum operator in one dimensional. Okay, so now we could also write a general operator x. Okay, or let's say this is a position operator x hat. So now we will do this x hat, and now this operator form of x hat is x. So this is the expectation value of your position operator. Okay, so what we have noticed that the operator is always sandwiched between psi star and psi and integrated over entire space. Okay, so now what we have convinced that if you want to know the state of a particle, we need to solve this so-called time-dependent Schrodinger equation, and this is the form which we have seen in one dimensional, and we want to write down this equation in 3 dimensions, then this quantity will be replaced by a del square operator, okay, where del square is a Laplacian. What is this? Which is d2 over dx2 plus d2 over dy2 plus dt over dz2. Okay, so now before we proceed further, let's have one question which you need to answer. Okay, so this is what we have seen where we want to talk about the dynamics of a classical particle. This is the equation of motion, or Newton's second law, which is a second order differential equation in time with respect to position. Okay, or when we want to describe the dynamics of a classical wave, this is the wave equation that we have seen in the earlier classes, that this is the second order differential equation with respect to position and second order differential equation with respect to time. Now if you want to describe the dynamics of a quantum particle, this is the Schrodinger equation that we have seen just in the previous slide. Now here you see that this is the first order differential equation with respect to time and second order differential equation with respect to position. The question is why so? Why this equation has a very unique form, that it is a second order differential equation with respect to position and first order differential equation with respect to time? What is so special about it? So let's move on. So this is the differential equation, let's say our time dependent Schrodinger equation. And now what we are going to assume here, that let's say this potential is independent of time. And once this is independent of time, then this psi, which is a function of x and t, can be written as a product form, that this function can be written as a product form of a spatial coordinate times temporal coordinate, or function of a temporal variable and function of a spatial coordinate. Okay, and this is what is known as separation of variable, which you will see most probably in coming classes of electromagnetism, where separation of variables are routinely used to solve different kind of problems. So what we can do, we can substitute this form of psi, which is written in terms of the separation of variables, into this equation. So what you will get in the left hand side when you substitute here, this is a differentiation with respect to time. Okay, so the spatial coordinate will be unaffected. So what we will get, I h cross phi x d chi over dt, and this is a differential equation with respect to position. So the time part will be unaffected. So what we will get, minus h cross square over 2m times chi of t d2 phi over dx2. So this is what you have got it, and here we have substituted as it is because there is no particular operator form of this potential at this point of time. Okay, so this is the equation that we have got it. Here phi is not going to be affected, so it is out of this operation, and here psi is not going to be affected, so this is out. So now what we can do, so this is what we have seen. Now we can divide the whole equation by phi psi. Okay, so when you divide this over phi psi, so what you will get, phi will cancel out and 1 over chi will come here, and here what you will get, 1 over phi will come here. Okay, and this is going to be independent because phi chi will come here. So what you have now noticed, that your left hand side is only the function of chi, whereas the right hand side is only the function of phi, and in this way you have separated the total equation. Okay, so this is only true when this is equal to some constant and this is equal to some constant. So let's call this constant as E, and later we will learn why we have called this constant as E, or let's say energy. Okay, so let's first simplify furthermore to the left hand side. So in the left hand side, what you are going to get, IH cross 1 over chi d chi over dt is equal to E. Now what you can do, you can take all this thing here and perform the simple integral. So that's what you will get an equation. And right hand side, what you are going to get, minus h cross square over 2m 1 over phi d2 phi over dx2 plus v is equal to E. This is what you have got it. Okay. So now once you perform a simple integral here, then it is very easy to see that your chi of t is equal to e to the power minus I e over h cross time t. Okay, this is the solution of this equation. Now we have to solve right hand side. Okay, so this is what we have seen. Okay, now what we can do, we can take this phi. So here you will phi, here you will get phi. Okay, and this is what we call as a time independent Schrodinger equation, because there is no involvement of the time, and we have already assumed that your potential is time independent. So this is time independent. So what we have done, we have simplified our time dependent Schrodinger equation into time independent Schrodinger equation. Okay, now we cannot solve this equation anymore unless we know what is the form of the potential. Okay, so in the coming classes we are going to do number of examples where we will give different form of the potential, and we will see what are the new physics we are going to learn in this quantum world. Okay, so that's what we are doing. So now let's ask, what is so special about the separable variable? Okay, so this was the separable variable, that your total psi was written as a product of the phi times chi, where phi was only function of x or r and chi was only a function of time. So why this is so special, and what is the new physics, or what is underlying physics about it? So there are three answers. Two are physical in nature and one is the mathematical in nature. So let's discuss. Okay, so this is what we have written as a separation of variable, and this is what we have seen, that the chi of t can be written as e to the power minus I e over h cross time t. So this is the total wave function, where phi of x time, this time dependent part. Okay, now let's ask, what is the probability density at time t is equal to t1? I hope that you now remember what is the definition of the probability density. So this is the modulus square of psi. Okay, so the probability density is the modulus square of psi, and now at what time t is equal to t1? So I have substituted t is equal to t1, which I will denote as a rho x and t1. So I said that when you say psi mod square means psi star psi. So the first term when you take psi star means phi star, and this minus I will be plus I because you are taking the complex conjugate, and now another time your psi, so phi of x time the same thing. This part will cancel out, and the total you have left with phi star phi, which is nothing but a modulus square of the phi square, modulus square of phi of x. Okay, so your probability density of a given function at time t1 is time independent. There is no time left here. Okay, now what is the probability density at time t is equal to t2? Same exercise you can do, and you can see that again your probability density is time independent. So what you have noticed, that the probability density does not depend on time when your solution is in this following form or the product form. Okay, now we can ask, what is the expectation value of an operator O in this state psi of xt? I hope now you have know what is the meaning of the expectation value of O. So when we need to sandwich this O operator in between the psi star psi, okay, so this is how you write your expectation value, psi star psi. Now I can write down the expression of psi star as a phi star E O phi of x, this one. Now remember, this integration is done with respect to dx. Okay, so this variable and this variable I can move anywhere because they are not x dependent. Okay, so this will drop it out, and what you have left with only phi star O phi dx. Okay, so what you have noticed, that your expectation value of any operator O in this psi of xt, where psi of xt is in the product form, is independent of time. Okay, this implies that expectation value of the position, energy, momentum operators do not change with time in these particular states. Okay, so then we can call this particular form of this state or wave function is a stationary state, because it remains unchanged whatever observation you are going to make, whether you are going to talk about the probability density are going to talk about the expectation value of any operator. These quantities are not changing over time or with respect to time. So then this state can be called as a stationary state. Okay. Now let's look this particular time independent Schrodinger equation again. Okay. Or equivalently, I can write down, I have taken this phi out. So this I can call out. And this quantity which I have written in this big bracket is called Hamiltonian. Okay. So I have written down this quantity in operator form. So this is P square over 2m plus V operator times phi is equal to E phi. And this big quantity is called Hamiltonian, which is the sum of the kinetic energy and potential energy operators. Okay. So in a very compact form, the time independent Schrodinger equation is written as H phi is equal to E phi. This is very easy to remember, where H is the total Hamiltonian of a system. Okay. So now let's find out the expectation value of this Hamiltonian H. So we know what is the definition of expectation value. H is sandwiched between psi star psi. We know that this psi star psi will give you exactly as a phi star phi. And from the previous equation, let me go back. You know that when H is operating on phi, it will give you E times phi. Okay. So this is what we are going to use it here. When this H operate on this phi, it will give you E times phi, and E is a constant. Okay. So this does not depend on this integration. So I can take this E out. So I have taken E out, and what is left with you? Phi star phi dx, and I assume that your phi star phi is so I assume that your phi is a normalized wave function. So phi star phi integration over entire space will give you unity. So you are left with E. So the expectation value of an operator in this basis is energy. Okay. So what we have learned that the separation constant which we have used earlier, E, we chose it as a total energy of the system. Okay, in the state sign. Okay. Now we can calculate what is about H square. So we can do the same mathematics. H square expectation value is psi star H square psi. Now I have written my phi star H square phi. Now H square can be written 2 times H. So one time H will multiply will give me E phi. Another time H will multiply with phi will give me another E phi. So what I will get? I will get E square times phi star phi integration over entire space. So I will get A square. Okay. So this is what I have just narrated down here. Okay. Now I can compute the uncertainty, or let's say the this delta of H, which is defined. I hope you remember this definition from the uncertainty principle lecture. That delta of H is defined as expectation value of H square operator minus expectation value of H operator square, and we know that both the values from the previous slide. So when we substitute this, it comes out 0. So what it implies that every measurement of the energy yields exactly the same value E. So there is no uncertainty involved in this energy. Okay. Thus the separable solutions of the time dependent Schrodinger equation psi are, let's say, equivalently phi, which is the solution of time independent Schrodinger equation, are these are the solutions are known as states of a definite or fixed energy. Okay. So now there is another final question. What about the other solutions of a general solution of a time dependent Schrodinger equation? So let's say we will learn in the coming classes that time independent Schrodinger equation gives infinite collections or infinite solutions ranging from phi 1, phi 2 and so on phi n with their energies E1, E2 and En. Okay. So any solution which is the linear superposition of these phis with their corresponding weightage of the time dependent factor and their weighing coefficient will also or can be called as a solution of this time dependent Schrodinger equation. And there are these coefficients which will let us know what is the weightage of particular states or particular wave functions in this combination. Okay. So let's recall what we have learned about the stationary state. So stationary state is a state with constant position, momentum and other physical parameters and definite energy. Okay. So what we can call as a consistency implies that the average value of the corresponding operator does not change with time. So this is the meaning of the consistency of an operator, that it does not change with time. So what it means, the definite value of a physical parameter means that the state in an eigenstate of the corresponding operator with a fixed eigenvalue. Okay, so we have to verify this. So let's have a state at particular time t. So this is the state, total state, which is a function of position and time. This is a some constant square root of 2 over L. This wave function you will see in coming classes why this is so special. We have just taken a form of the function. What is the implication, where it is used, we will see in coming classes. And this is your energy dependent vector. Okay. Now let's see what is the expectation value of this momentum operator in this particular given state. So we can just substitute this value phi n star p phi n dx by following the definition. We see that this energy dependent factor will cancel it out, so it will only remains with this one. And then we can easily see that with this function that this expectation value of p is 0. Okay, so as we saw before, it is true for any operator O that if you take a expectation value of an operator at time t, it is same as expectation value of the same operator at time t is equal to 0 in this stationary state. Okay, the same we can talk about expectation value of h. So we just substitute this one, and here we are taking a specific integration limit. We will come to know. For the timing, let's think about a mathematical exercise, because this function, the function that we have seen here, is defined between 0 to L, and otherwise this function is non-zero. So that's why we have chosen this particular limit instead of minus infinite to plus infinite. Okay, so by following the psi of xt and using this definition, psi of xt as different cn's phi n and e to the power I, and that's what we are going to substitute here. So here we are going to write down as there will be one summation of this summation over n cn star phi n star, or let's say cm star phi m star e to the power plus I e m t over h cross, and here there will be summation over n. So there are two summations, there are two coefficients, and these are the two energy independent. And now note that this em and en are different, so they cannot immediately be cancelled out. However, they are independent of this integral, so I'm allowed to take these values outside. And now when h will operate on your phi n, it will give you en over phi m. Okay, so this is what I have done, and now this is left with this one. Okay, now this is another concept that we are going to learn in this class, that if you have the two wave function, and this is a wave function for a given system, or let's say the expected wave function, so they will show what is called the orthonormalization. It means that they have to be non-zero when m is equal to n, and when m is not equal to n, this has to be 0. So that's why this delta functions comes out, and you know this delta function definition from the class of Fourier series. This is 1 when m is equal to n, and when m does not equal to n, then this is 0. So only the non-zero value comes when m is equal to n. So m is equal to n means you have to replace this m here n, so this will be cancel it out. There will be only one summation, so this comes out. Okay, so what it means that in this generalized states, which is a linear superposition of so many states of phi's with their respective time dependent factors and corresponding coefficient, the expectation value of this Hamiltonian, or let's say the average value of this energy in this generalized state, is the sum over eigenstates or sum over energy per corresponding phi n weighted by their coefficients. Okay, and which is a time independent quantity. So this we have also verified it. Okay, so now let's ask few more questions before I end today's lecture. If expectation value of h remains constant over time, is psi of xt is a stationary state? The answer is no. The implication other way around is not true. Stationary states are eigenstates of h, so they have a definite values of energy. Here we see that h remains constant, but psi of xt is not an eigenstate of it. That's what we have seen in the previous lecture. Okay, now if the answer of A is no, that's what we have seen, then why h remains constant over time? The answer is that's just stating the statement of conservation of energy in the language of quantum mechanics. Okay, I hope that you have learned some new concept. Please go through these slides. Okay, and we will start applying all these concepts for a given problem or for a given potential which mimic a particular kind of a system. With that, let me suggest the recommended readings for this particular class. Schrödinger equation section 6.1, 6.2, 6.3 from this book. Thank you very much and see you in the next class.